For over a century, the power grid ran on momentum. Industrial generators, massive, heavy hydroelectric and coal turbines, provided electricity by spinning tons of raw iron. That immense physical weight gave the grid a natural kinetic stability. To manage a system this massive, engineers relied on a specific kind of math, Positive Sequence Phasor Domain, or PSPD, modeling. It takes a complex system and assumes a quasi-steady state, treating the electricity as a perfectly balanced repeating sinusoidal wave. PSPD calculates these conditions at the grid's fundamental frequency of 60 Hz. By treating the current as a smooth, predictable rhythm, engineers can efficiently calculate large-scale power flow and track stability across entire continents. Because the physical equipment was bulky and slow to react, standardizing on this steady-state math made perfect sense. The slow, analog calculations matched the sluggish, reliable nature of the spinning machines. Today, we are stripping that heavy iron off the grid. Massive solar and wind farms are replacing physical turbines, shifting power generation away from kinetic hardware entirely. This table breaks down the differences between legacy generation and these modern inverter-based resources, or IBRs. Notice the left column. Modern solar and wind plants have little to no physical inertia. Their electrical output is managed entirely by power electronics and software. This is where the legacy math breaks down. Inverters process changes through software loops that operate in microseconds. PSPD calculations, however, take mathematical snapshots in milliseconds. The simulation is simply too slow to capture the software's behavior. Look at this chart mapping operational bandwidths. Down below 10 Hz, traditional models capture slow adjustments, but the fast converter controls and phase-locked loops of an IBR operate in the 1 to 10 kHz range. They exist entirely outside standard modeling bandwidths. By using slow, analog math to evaluate a hyper-fast, digitally controlled power network, engineers are staring into a massive resolution gap, a mathematical blind spot where highly destructive electrical failures can hide. In a standard simulation, grid voltage looks like a perfectly smooth, continuous 60 Hz sine wave. But if you zoom in to the microsecond level, you find that the actual waveform is chaotic, filled with jagged, erratic, high-frequency spikes. These microspikes introduce a unique vulnerability called subsynchronous control interaction, or SSCI. SSCI happens when an inverter's high-speed software control loops accidentally sync up with the grid's natural resonance at lower frequencies. The inverter reacts to the grid reacts to the inverter, and those tiny, jagged spikes quickly compound into violent, expanding oscillations. Because legacy PSPD math assumes a perfect sine wave and only checks the data every few milliseconds, these hyper-fast oscillations slip entirely between the calculation frames. The simulation registers a calm system. Ignoring these sub-cycle dynamics leaves grid operators completely blind. Resonant instabilities can build up and violently tear the system apart from the inside out, while standard engineering models show zero signs of danger. We see this destructive potential clearly in offshore wind farms. These massive installations push enormous amounts of continuous power through dense, complex networks of medium-voltage collector cables. To protect these networks during electrical faults, engineers use vacuum circuit breakers, or VCBs. Their compact design allows them to reliably sever connections to stop massive surges of fault current. However, VCBs are prone to incredibly fast switching transients. When they interrupt a fault, it generates transient recovery voltage, a sudden, high-frequency voltage surge across the breaker contacts that can cause the current to chop and repeatedly reignite. Again, steady-state math assumes a perfectly smooth line and entirely misses these microsecond electrical spikes. A PSPD model will not warn you that these high-frequency reignitions are systematically degrading the physical insulation inside your step-up transformers. This creates a terrifying reality. Standard safety simulations will output clean data and confidently declare the grid is perfectly stable, even while microtransients are actively destroying millions of dollars of physical hardware. Fixing this blind spot requires abandoning steady-state math entirely in favor of a much heavier computational approach, electromagnetic transient,
or EMT, modeling. Instead of relying on simplified phasor approximations, EMT drops the assumption of a balanced sine wave. EMT software solves the entire system's actual differential equations in the time domain. It computes the exact voltage and current behavior point by point, calculating the true electrical waveform at incredibly small microsecond intervals. This diagram illustrates the specific use cases for EMT studies. By acting as an ultra-high-speed camera for the grid, EMT allows engineers to accurately test complex inverter write-through capabilities and pinpoint control instabilities before they ever touch real equipment. But closing the resolution gap comes at an extreme operational cost. EMT simulations require massive computational horsepower, taking hours or days to calculate what a legacy simulation solves in seconds. It also demands total transparency from hardware manufacturers. Engineers can no longer use generic approximations. They need highly detailed, bespoke software models of the exact code running inside each specific inverter.
Because fast control loops interact across long distances, planners must meticulously map networks deep into the surrounding grid, sometimes modeling individual substations up to 9 buses away just to screen for hidden resonance. Maintaining grid reliability requires seeing the system as it actually behaves. As massive turbines give way to high-speed power electronics, our calculations must evolve from comfortable, steady-state assumptions to microsecond time domain reality.